Seems kind of thin in here, doesn't it? All right, so we're going to do 7.2. This is called volumes. And I'm going to add something to this title, volumes of solids of revolution. All right. Y'all ready? All right, today's going to be stepping into new territory here. Really, pretty much up to this point, everything that we've done, you could argue could be done on a computer. Like if you go to Wolfram Alpha, you could have done all the integration that we've done. And we almost feel like the computer is almost a little smarter than us because it can do all this stuff that we can't do like this. And it'll do our definite integrals, right? If we plug in endpoints, it can do that. It can actually handle improper integrals where you have infinity on your limits of integration. So we've been kind of humbled by the computer a little bit, thank you. But this is really kind of the first section where, yes, the computer can help us, but not till the very end when we actually get the integral. The setup of the problem requires some critical thinking. And this is the first time that we're actually going to be investigating things that are three-dimensional. So we're going to kind of get a little bit of a test for your brain here, how your spatial sort of recognition is. Like how comfortable are you seeing things three-dimensionally, even if they're not actually three-dimensional, they're on a flat sheet of paper. So we'll see how it goes. Volumes of solids of revolution. So this section, to start us out, we're going to need to get some preliminary things out of the way. Just some formulas that we should, in some way, shape, or form, be comfortable with. First of all, what is the volume? And remember, volume is not area, right? Area is what we use to describe two-dimensional objects. Volume is what we use to describe how much stuff fits inside of a container that's three-dimensional. So if we have a box, right, a three-dimensional box, then this box here, right, does that kind of look three-dimensional to you? My goal was to try and make that look three-dimensional. Whoa, what's going on? Stop. Then the technical name for this, it's actually called a parallelepiped. That's the math term, the math lingo for a box. And if we know the three sides, if we can measure the three sides, so maybe the length, the width, and the height, then the volume of that is just length times width times height. We're all good with that? No problems? All right. Now if we change it up a little bit and we take a look at a cylinder, so here's a cylinder in three-dimensional space, then we can also find the volume of this. And does this formula look familiar? Volume is pi r squared times h. So h here would be the height or the thickness of this disk, right? And then pi r squared, doesn't that look familiar, pi r squared? Pi r squared is the area of a circle. So if that's the radius of this cylinder, then we're really just computing first the area of this cylinder, or that circle, and then multiplying it by like how deep that is, right? And that gives us our volume. We good? Yeah? Okay. Another thing we want to look at here. What if we have a cylinder? Now these are really like flattened out cylinders, right? Normally when you see cylinders, they're really tall and narrow, right? Like a beer can or something. But the cylinders I'm looking at look like that for a reason, all right? We're almost going to look at this thing as being, we're going to call it a washer. Because like if you've ever worked with tools, bolts, you know, then you have a washer that you put, then you put the bolt. Well, that kind of looks like a washer, right? And the volume of this should be equal to the volume of the big cylinder without any hole drilled out of it, right? And then take away the volume of the smaller cylinder, which is that piece that we took out, right? So you can see from this formula that what I've done is, I'm talking about right here, whoa, right there. The volume is equal to pi r out squared times h minus pi times r in squared h. So what that means is this. If you take the big cylinder and call this radius r out, what I meant by that, or what I mean by that, is it's like the outer edge, right, of the cylinder. Take that radius, square it, multiply times pi, that gives you the area, and then how deep this is h. So that gives you this. And then if I call the radius of the smaller cylinder r in, then of course the volume of that would be pi r in squared times h, right? Subtract the two, and that should be the volume of that little washer. Do you all agree? Okay. Now this last piece here, all I did here was factored out a pi. So since both of these have a pi, I factored it out and put it out front. And then I also factored out an h, but I decided to throw that in the back. And you'll see why in a little while, why I put the h back here. I could have put the h out here with the pi, right? Okay, any questions on that? We're good? Okay. This last one, we're going to skip for now. I'll come back to that. Now we're ready to start. We are going to start this out by trying to figure out the volume of something using what's called the method of disks or washers. Anybody else have that take-home little assignment? This is kind of last call for it right now. No? All right, so let me try and give you some visual idea of what's going on here. All right, last class, our study of areas told us that if we wanted the area of this shaded region, that the area would be equal to, in this particular case, these are both functions of x, right? So you would do, what would this be? You remember just straight to the formula what this would be? Yeah? Integral a to b f of x minus g of x, very close, missing something, dx. Okay, just that, right? That's it right there. And the f of x minus g of x, remember that was when we just grabbed like an arbitrary rectangle. We said, well, how tall is it? Well, it's the f, take away the g, right? And how wide is it? dx. And we said, okay, take that. This is the area of one little sliver, and add them all up, and we have the integral. So were y'all all okay with that idea from last time? Okay. What we're going to do now is something completely different than this. We're going to somehow create some volume out of this, which means we need a three-dimensional picture. So imagine taking this region and rotating it around the x-axis. Can you all see that? I don't think you can see it. Not necessarily. So here's what I'm going to do. First, I'm going to kind of pop this into three-dimensional space. So I'm going to come at it like with a little angle, and then I'm going to start wrapping this thing around the x-axis. Here it comes. Okay? Do you see this solid? You all see that? We want the volume of that. That seems like kind of a tough question, right? And then let me do this. I'll kind of make it semi-transparent so you can kind of see that on the inside we do have a hole, but it's not just like a straight hole through it. It curves up because that's being formed by that bottom function, right? Everyone good? Now is it obvious? So how in the hell are we? I don't think hell's a bad word. I hear it on the radio. I hear it on TV all the time. I don't think that qualifies. It doesn't qualify.
I feel like you stopped yourself, so it should qualify. You know
because I shouldn't talk like that, but
just saying, you call
yeah.
yourself
I know. You know what? No, it's not going to qualify. Sorry. It has to be 4-letter words. Oh, okay. All right, so let's try and get to a formula. Here's our formula. We're going to get to it, but let me try and help with another picture. All right, I'm going to do something similar to what we just did in that picture, revolving it, except let's just look at one curve instead of two. All right, let's just take this very basic idea. Last class, we just found the area of that, found a formula for it, used the integral to add them up. What I'd like to do now is find a formula that will represent a volume of one sliver, one slice, one cross-section of that solid. What? Okay, so let's do this. Let's take this rectangle. I'm going to, again, oh, come on. Come at it from the side here. Kind of have to move things around. Boy, I'm having trouble. There we go. I'm going to take that rectangle, and I'm going to rotate that rectangle around the x-axis. All right, now that's kind of hard to see. Does that make sense, though? Yes? Then the question would be, what's the volume, right? Not the area of a rectangle anymore. Now I've created like a disk, haven't I? And I'd like to know, like, what is the volume of that one little sliver? What's the volume of this? Well, it's a right cylinder, right? We did this earlier. This is one of the formulas we went through. That's pi r squared times h, right? Pi r squared times h is the actual formula for that. And imagine now that I do this for a bunch of rectangles. So I had one rectangle. I'm going to do a bunch of them in here. Just like we did Riemann sums, we had like an infinite number of rectangles in there. If I do this and spin all those rectangles around, then I'm going to get something like that, right? Yep. Bunch of disks in there. And then when we do the integral, we're basically letting the number of those go to infinity, aren't we? And the more you have, the better the approximation is going to be, right? Until eventually you get the actual thing you're looking for, which is this solid. It looks kind of like like a football or a lemon. Do you all see that right there is the blue curve rotated around the x-axis? But the concept is that we're still going to look at this individual slice. Where did my slice go? Oh, I pulled the wrong one back, sorry. We're going to take that original slice and just look at it geometrically, turn it into a disk, and then add all those disks up. Simple enough? All right. So help me out with the formula for this. Do you know this little width? dx, right? Because dx, that comes from the width of the rectangle, and that's been dx in the past, so it may as well be dx now. And the only other thing you need to know is the radius, right? So think about if you're rotating around this axis, right? If that's your axis of rotation, then the distance from here to this top edge should be your radius. And what is that for us here? It's the function itself, right? It's the height of the function. If we call this f of x, then this is going to be f of x. And as we move the rectangle, this will shorten or get taller or shorter depending on where our x is, right? So the distance from here to this top edge right there, our radius, is going to be f of x. Got it? So the volume should be pi, right? The radius, f of x, that function squared, dx. See it? Pi r squared times h. That will give me the volume of a single sliver. And as before, now how do we add them all up? We do an integral. And that integral is going to start out where? Going from where to where? Well, we would need to know these points, right? So in this case, it looks like 0 and something. Let's just call it a and b, just for the sake of demonstration. So this will go from a to b, right? And then this, right? We're adding up each of these. Now, pi is a constant, so that can just come out. And then we just have the function squared dx. Interesting, right? If you compare this, let's compare that to last class. If I asked you for the area underneath this curve, your formula would be integral a to b, just the function, right? F of x dx. This would give you the area below that curve. This, with the pi in there and the squared, actually gives you the volume of the solid of revolution. See where the title comes from? It's a solid of revolution. Revolution. All right.
So it's always x squared?
Pardon? Use your right arm. Revolution. Or left. No. What were you saying? I'm sorry.
Is it always going to be like squared, not like cubed?
Oh, it'll always be squared because the formula for the cylinder, right, was pi r squared times h, so it will be squared. Now, if our function itself is something like x squared, then we're going to have to square it to become x to the fourth. Or if our function is x cubed, then we have to square it to become x to the sixth. So the function is going to dictate what this turns into. Sorry, this. But this is like the general setup for it. Got it? Okay, now I went a little easy on us here on this first one because on the original picture I gave you, wasn't it two functions? Wasn't this two functions? And so I would like to try and generate our general formula now with this concept instead, because this is the more powerful one. So this is what all this gibberish means here.
This is just for a washer, right?
This is what we call the washer method. Now, in the problem I just did where we generated that formula, we created disks when we did that, right? When we spun the rectangle around, it created a disk, which you could argue is a washer with no hole in it, right? A disk is a washer with no hole. So you could call a disk a washer, maybe. Is a square a rectangle? Technically it is? Okay. All right, so here's our setup. We are going to look at this picture here. This picture right here should look completely like last class. There's no difference, right? With one small, well, there is a small minor difference. That little symbol right here. This is two kind of curved arrows that go like this. It's supposed to give you this idea that there's a rotation occurring. So I'm taking this region, I'm rotating it around the x-axis. Now, last class, I was asking you to get comfortable with the idea of moving this rectangle out to the side and trying to identify pieces of it. You're about to see why as we start to step up the difficulty of these. But that's what my standard practice is going to be to do that. I'm going to take this, move this over. Notice that this x-axis is my axis of rotation, right? This is what I'm rotating around. I'm always going to use a dotted line to represent my axis of rotation. So there's a dotted line. And then when we take this region, this rectangle, and rotate it, we get this. That's a washer. Can you all see the washer? I don't think it's a very good washer, but I'll try it again over here. I'll exaggerate it a little more. That better? Now, that rectangle right here actually lives inside of this washer, right? And it got spun around, something like that. And if I want to know the volume of this washer or that washer, then I need to know really three things. I need to know how wide it is. So how wide's the washer? Dx. Okay, so that's good. That's not going to be anything different. And then I need to know what other two things? Yeah, I need to know the inner radius and outer radius. Go back to the picture we had here. This one right here. Remember that? Didn't we say if we want to know what the volume of a washer is, that, we have a cutout in the middle. You need to know an outer radius and an inner radius, and you need to know h, the height. So for us, the outer radius is the distance from the axis of rotation to the top edge of this rectangle, right? And the inner radius is the distance from the axis of rotation to the bottom of our rectangle. So that's why I think it's important for us to actually look at this picture. Because this picture right here isn't this right here our R out, f of x, or